Okay, so yesterday we started 8-1, and Autumn said she got to about 30, and they were just kind of coming. We do have some situations where we have to be a little bit more manipulative to the problems so we can make them fit. And we ran into that once in a while when we went through the rules. But now it's just going to seem like more often just because we have all the rules that we're using. So the first example we're going to start with is the integral of x squared divided by the square root of 16 minus x to the 6th dx. So again, that x is going to bother me. You need to be looking at all your rules. Hopefully you have your sheets handy. So what does it think? You know, you're 20, right? 20 possible rules.
It's looking like arcsine.
Okay. Do you agree with that one?
Yeah, like arcsine on steroids.
Yeah, it a little bit arcsine like steroids, right? Because arcsine needs to have a squared minus u squared, doesn't it? So that would make a being what? 4. And u being x cubed. Okay. So did I write that right? I want to make sure I wrote it down right. Yep, I did. Okay, so if that is the case, then what would du be then? Because 3x squared, because so we're close, right? We've got our x squared that we need. We're missing what? 3. So how did the 3?
1/3.
It was 1/3. The integral. And we now have, oh, well, I'm going to have to put that du up there. That's going to be gross, isn't it? Over that 4 squared minus u squared. So 1/3 of the arcsine of what?
It's going to be, is it x cubed over 4, u over a?
Yep, it's u over a. X cubed over 4. Plus c. Because remember the arcsine. I didn't write it like I was doing yesterday, did I? I think you used trig functions a couple times through 30, didn't you? Mm-hmm. Okay. And it feels like when you're doing these rules that you use a lot of trig signs, you use a lot of logarithms. Some of the ones that we didn't feel like we did a lot of, but they're kind of easier to use once you identify the things.
So that all this is just unintegrating it? Like this section?
And integrating is derivative. And derivating it? All it is integration. Because in 8.2, we start by parts. So we're going to have to pick it apart into things. And it will kind of look like a product rule as we're doing the integration. And so we want to make sure that we're solid in our integration and picking techniques. Because we're going to have to do, we have to do the derivative of part of it and then the integral of the other part of it. So you kind of do both. So we want to make sure we're strong on those. That's why we're devoting a whole week.
Is that exciting?
You asked. Okay. So now we're going to have the integral of 1 over 1 plus e to the x dx. You guys have to remind me to move up. So what are we tempted with? Like,
Is it another trig one? No.
well, when I see a fraction, if I can't fit a trig one, I'm looking for a what?
U prime over u.
The u prime over u, which would be logarithm.
Yeah.
Okay, so if it was a logarithm, then what would u be?
1 plus e to the x.
So 1 plus e to the x. So du, or u prime. Do you guys want du or u prime? Does it matter when you see them? Okay. I switched back and forth in one problem. So u prime would be what? E to the x. We do not have an e to the x, do we? What?
So that's the wrong one.
Well, no. Sometimes we can manipulate things. Remember, like teenagers are master manipulators. We need to work on the math problems that way. So if I put an e to the x in the numerator, could I do that? Could I just say plus e to the x?
I suppose.
Well, if I said plus e to the x, what would I also have to do in there not to change the problem? What's the only...
To the bottom.
No, I'm not multiplying, I'm adding. So what's the only thing you can add and not change a problem?
You have to subtract it.
You have to subtract it, because the only thing I can add without changing a problem is 0. So if I add it, I also have to subtract it. So I changed how the problem looked, but did I change the problem? No. So then we probably want to tear it apart like we did yesterday. And the part I want to tear apart and leave, I want to have e to the x over 1 plus e to the x. That was the whole point of this. Correct? So this is going to be in one fraction, and we're going to leave this in the other fraction. What's going to be the advantage of having 1 plus e to the x over 1 plus e to the x? What do I get? 1. And that's going to be really nice to integrate, right?
Yeah.
So I now have the integral of 1 plus e to the x over 1 plus e to the x dx. I always forget my dx is in the middle. And then e to the x over 1 plus e to the x dx. So now our second integral fits that natural log, doesn't it? Okay, so what is the integral? Well, you want to rewrite this as 1, or can we just say that's 1? That's 1? Okay, so what's the integral of dx then? X. And then minus, well, this over here fits our u and u prime, so that's what rule? The natural log. Absolute value. Now, but do we need an absolute value? Well, I have 1 plus, so I'm good there, right? Is e to the x ever going to be negative? No, because what does a negative variable do? I mean, a negative exponent, it doesn't make it negative, it reciprocates it. So is that ever going to be negative? No. So 1 plus e to the x plus c.
Can I put it in an absolute value?
You may. That's fine. And I was just going to bring that up. You can write it as the absolute value of 1 plus e to the x. But I'm going to tell you, if you ever deal with a mathematician, they are going to laugh at you. Okay? Why are they going to... I do laugh at you some days. Why are they going to laugh at me over this?
Because you don't need it.
Because I don't need it. And remember, they're efficiently lazy, right? And if you leave it like this, they're going to think you don't know that you don't need it. Does that make sense?
And there's nothing wrong with that, though.
So I would accept the absolute value, and I, for one, usually always write the absolute value, and then I stop and I think about it, and I'll take it away. But it's not wrong to leave the absolute value there. Like if I said the absolute value was 6, the answer is what? 6?
Oh.
It's basically not doing the operation by leaving it there. Does that make sense?
Yeah, but it doesn't really matter.
No, it does not really matter.
Okay, that's good.
So, but when that mathematician, when you're working on your math doctorate and they laugh at you, you let me know.
Doctorate?
Yes, your math
If I didn't
doctor.
get my doctorate in math, you better call a hospital if something went wrong.
Okay, we got one more example. We haven't done any, well, we did this trig one. We did the trig where it fit the rule trig, but we haven't done the trig when it's in the integral yet, have we? So we found those kind of tricky, if I remember right, when we were doing them just by themselves. So I wanted to make sure we did one. So I have the integral of the cotangent of x times the natural log of the sine of x dx. So the first thing we need to identify is what? U and du. We got a couple options, don't we? Yeah. We could say cotangent, because that's multiplication, so either one of them could be right. So I could say cotangent is my u. What would u prime then be?
I can tell you.
Yes.
Negative cosecant squared.
So it'd be negative cosecant squared.
Yes.
Did that give me anywhere I need, like, no, that is not helpful. And we've talked about that. Sometimes we pick a u and it's not the right u. And that's okay, because we're thinking about what we need to do. So that isn't anything even close to what this is. And that's not where we want to go then. So what's our other possibility for u then?
Sine. That one I know.
Well, it's actually, it's the whole thing. The natural log of sine. So then if I have the natural log of sine of x, it just is killing me not to put a parentheses just around the x.
Don't do it.
So what would u prime then be there?
U prime over u, so cosine over sine.
Yes.
Negative. Wouldn't it be negative?
Well, it would be the derivative is you got to do the derivative again, right? So it'd be the derivative sine over sine. What's the derivative of sine? It's negative on the cosine. Derivative of cosine is negative sine.
That is literally a trick.
Only if you don't know it yet. Okay, so the integral is cosine over sine, which is what, guys?
Cotangent.
Cotangent. Does that get me somewhere? Yes. That gets me where I want to be, doesn't it?
Unless you don't want to be there.
Well, I think I want to be there. So this is now just the integral of u du. So this mess all down nice and neat to here. Isn't that nice to see? Okay, so what is the integral of u?
Wait, didn't we already do that? It was just
No.
cotangent.
No, the integral of u. Like
Oh, yeah, the integral.
basic integration.
Okay, so let me look at me.
Add 1, multiply with our reciprocal.
You mean add one?
Add 1.
Okay, so,
So
we're
it's-
using exponents.
Yeah, we're just
So
it's just
1/2 u
1/2 u squared plus c.
Oh, we're not plugging that.
No, we will plug back in, but I want you to see that. This is the very first day of integration, isn't it?
Yeah.
Yeah, and we wanted to make it all hard. It's not. So now we have to replace back in u. Yes, that is correct, Natalie. And what is u?
Natural.
Okay, so this was a no, right? So the natural log of the sine of x.
Squared.
I've got to put it there. Sorry, guys.
That looks bad.
What looks bad?
Just in parentheses.
Actually, that squared isn't right. Because that squared is only squaring this. What's it need to square? The whole thing. So I need to put some brackets there. Oh, you already put brackets? Because you put brackets and then a parenthesis, didn't you? Because you couldn't resist.
Oh, I did that too.
So we can use parentheses again, right? We can have multiple parentheses. It's just nice to break it up. So this, I put it there. I wanted to make sure we went through it because we hadn't done one with the cosine, the trig from the beginning. And again, to throw out, I knew you'd first want to do u as cotangent. We always want to because it looks easy. But I think we've discussed using the harder one is usually the best decision for the u, right? Because it's more places to go. especially when the other part is bigger. There's one last thing I want to point out in the textbook. I have it pulled up. I finally yelled at them enough.
Oh, and look, her background's still not us.
No, it is. It's right here. I haven't found how to get both of you. It is. It's right there. I'm working on it. Give me a break.
You can't even see you two because you're so short. That's the way you're
You're so funny. Okay, so I wanted to point out this. So procedures for fitting integrands, I said that wrong, to basic integration rules. So you can expand the numerator. We did that. And this is just an example. This is all in your textbook on page 519 if you want to look at it. You have the separate the numerator. We did that today. We didn't do anything with completing the square, but could we do it? Yes, unfortunately, that is always an option. I will say you as well as I would always try to avoid that option, but it is an option to complete the square. But completing the square can be accomplished in different ways as well. They factored divide improper rational functions, so I could, what did they do here? I have x squared over x squared plus 1 equals 1 plus 1 over x squared plus, minus, excuse me. So we did a division. We did that yesterday. Did long division, yes?
Oh, yeah.
Okay, so we would do this when what? When that numerator denominator match greater than or equal to. And that was one of those techniques that we hit on, but it wasn't like a lot. But can you see that happening quite a bit? It does happen more than you want. But the division is actually pretty easy because you just put that remainder over here. Add or subtract terms to the numerator. Did we do that today? We did that e to the x. We added it and subtracted it. I feel like I'm not big enough. Am I big enough? And then they just show you further on how it broke down. Once you do that, but the key to that was we already decided what u was and u prime before we started adding and subtracting things in. Because if we start adding and subtracting things in, we don't know what we're trying to accomplish. And then using your trig identities, you can multiply. We have the Pythagorean. We have conjugates. Could we always multiply by conjugates?
Yeah.
Yes, because if we multiply those conjugates, we can use them more like a trig proof. So then we can start working with them. Okay? And these are just your basic integration rules that they're on that. You guys have them on your sheet, but did you look on page 516? They're all listed there. But you guys have your sheets, and I would assume all of those. Have you found a rule yet that wasn't on there?
Well, I meant to look through it last night.
Okay. I would encourage you, if you're not going to rewrite your sheet, you need to go through what you have and make sure all of these are available to you in an order that makes sense. Does that make sense? What I'm saying? And I usually can do derivatives and look at integrals and go backwards, but some of them I have to have the integral, like decide what you need on there so it's not overwhelming what's on there. I am. Sometimes you put a little much on there and then you can't find things, right? Okay. Do you guys have any specific questions from yesterday?
Nope.
Natalie? So Natalie will be starting yesterday's assignment.
I bet Kill didn't start it either.
He probably didn't. But he is not here for me to